first thing we're talking about is the log rule for integration. This says let u be a differentiable function of x. So the first part of this says the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. And this makes a lot of sense because if you recall, the derivative of the natural log function is equal to 1 over x. So the integral of 1 over x dx should be equal to the natural log of the absolute value of x plus c. Now I also get asked a lot, why is it the natural log of the absolute value of x plus c? Because remember, the natural log function is only defined for x greater than 0. So we can't have our x value when we integrate over here be negative because you can't take the natural log of a negative number. Now the second part of this says the integral of 1 over u du is equal to the natural log of the absolute value of u plus c. Now you may be thinking, how is this down here different than this? Well, remember, u is going to be a differentiable function of x. So we're imagining u to be x plus 5 or 2x plus 8 or 7x minus 9 or x cubed minus 5x plus 10. That's what u is equal to, a differentiable function of x. So what this is saying is that you can use u substitution in order to integrate 1 over u du, and it would still be equal to the natural log of the absolute value of u plus c.
I have 2 stomachs! It's example time!
Now example 1 says find the indefinite integral. So we're taking the integral of 1 over x plus 2 dx. Now we said anytime we're taking the integral of 1 over a function in terms of x, we can use u substitution in order to evaluate that integral. So we're going to set u equal to our denominator down here, which in this case would be x plus 2. Therefore, the derivative of this with respect to x, the derivative of u with respect to x is du dx. The derivative of x with respect to x is just going to be 1. Derivative of 2 is going to be 0. Multiply both sides by dx, we get du is equal to dx. We look at the problem, there's our dx. So we can then rewrite this integral in terms of u and du. We're going to substitute u in for the x plus 2. We're going to substitute du in for the dx. Now all we have to do is evaluate this integral using the theorem that we talked about before. The integral of 1 over u du we now know is ln, the natural log of the absolute value of u plus c. Then to finish evaluating this integral, all we have to do is take what we set u equal to, which was x plus 2, plug it back in for u, and we have successfully evaluated our indefinite integral up here. Per B, we are again evaluating an indefinite integral of 1 over a function in terms of x. And we said anytime we're evaluating an integral of 1 over a function in terms of x, we can use u substitution in order to evaluate that integral. So we're going to set u equal to our denominator in this case, which would be 4x minus 1. Therefore, when I take the derivative of this with respect to x, the derivative of u with respect to x is going to be du dx. The derivative of 4x is just going to be 4. Derivative of negative 1 is going to be 0. Multiply both sides by dx, I get du is equal to 4 dx. We look at the problem, there's a dx, but there is no 4. So what we're going to have to do is we're going to have to move this constant to the other side of the equation. So we're going to divide both sides by 4, and we get that 1/4 du is equal to dx. We can then rewrite this indefinite integral in terms of u and du. We can take u, plug it in for 4x minus 1. We can take 1/4 du, plug it in for dx. All we have to do then is evaluate this integral. To do that, we have to prepare it for integration. We're going to take this 1/4, move it out front of the integral sign, because that's just a constant. We can then integrate 1 over u du, which we now know is the natural log of the absolute value of u plus c. Multiply that 1/4 on, and then to finish evaluating this integral, all we have to do is take what we set u equal to, which is 4x minus 1, plug it back in for u, and we have successfully evaluated our indefinite integral.
Time to follow my pheromone trail back to the hole! You try!
Okay, doing the same thing, except this time I have the integral of x over x squared plus 1 dx. Interesting, my numerator is no longer a constant, so what do? Well, anytime you have a function being divided by another function, or a function times another function, you should always try to use u substitution to integrate. And when you do that, you're going to set u equal to whichever function. If you were to take the derivative of it, you would get the other function. So in this case, I'm going to set u equal to x squared plus 1. The reason is because if I take the derivative of this with respect to x, derivative of u with respect to x is du dx. Derivative of x squared with respect to x is going to be 2x to the first power. Derivative of 1 is going to be 0. Multiply both sides by dx, I get du is equal to 2x dx. Now we look at our problem. There's an x and a dx. Perfect. But there's no 2. So how do I get rid of that 2? Well, I have to divide it to the other side of this equation. Now what I can do is rewrite this indefinite integral in terms of u and du. I'm going to substitute u in for x squared plus 1. I'm going to substitute 1/2 du in for the the x dx. Now I have my indefinite integral in terms of u and du. So I can prepare this for integration and integrate. How do I prepare this? I take this 1/2, this constant, move it out front of the integral sign, and now I'm ready to integrate. The integral of 1 over u du, by the theorem we talked about previously, is the natural log of the absolute value of u plus c. Multiply that 1/2 to our ln, and now we're ready to finish this question. We're going to substitute back in what we set u equal to, which is x squared plus 1. We plug that back in for u, and we have our answer to our indefinite integral up here. Part B, doing the same thing. We again have a function being divided by another function. When this happens, you always want to try to use u substitution. We're going to set u equal to whichever function. If I were to take the derivative of that function, I would get the other function. So I'm going to set u equal to x cubed plus 8. The reason is because if I take the derivative of this with respect to x, derivative of u with respect to x is du dx. Derivative of x cubed is going to be 3x to the second power. Derivative of 8 is going to be 0. Multiply both sides by dx, I get du is equal to 3x to the second dx. Now we look at our question. There's an x squared and a dx. Perfect. But there is no 3. Anytime this happens, we have to divide that constant to the other side of the equation. Now we're ready to rewrite this indefinite integral in terms of u and du. We're going to substitute u in for this x cubed plus 8. We're going to substitute 1/3 du in for the x squared dx. Now we have rewritten our integral in terms of u and du, so we can prepare this for integration and integrate. We have this 1/3, which is a constant. We can move out front of our integral sign. We now can integrate 1 over u du. According to the theorem we talked about previously, the integral of 1 over u du is going to be the natural log of the absolute value of u plus c. Multiply that 1/3 on, and now we're ready to substitute back in what we set u equal to, which was x cubed plus 8. We plug that back in for u, and we have the answer to our indefinite integral up here. Example 2, doing the same thing. We are finding the indefinite integral, this time of secant squared x over tan x dx. So we are again taking the indefinite integral of a function being divided by another function. Anytime that happens, you should try to use u substitution in order to integrate. So I'm going to set u equal to whichever function, if I were to take the derivative of it, would give me the other function. So in this problem, I'm going to set u equal to tan x. The reason is because if I take the derivative of this with respect to x, derivative of u with respect to x is du dx. The derivative of tan x is going to be secant squared x. Multiply both sides by dx, I get du is equal to secant squared x dx, which takes care of that other function. Now I can rewrite this indefinite integral in terms of u and du. I'm going to substitute u in for tan x. I'm going to substitute du in for secant squared x dx. And I just have the integral of 1 over u du, which is super easy. Now I just integrate that according to the theorem we talked about previously. It's going to be ln, the natural log of the absolute value of u plus c. I then plug back in what I set u equal to, which is tan x in this case, and I get my answer to my indefinite integral up here.
Red answer scary. You try.
Okay, doing the same thing. I again am taking the indefinite integral of a rational function where it's a function being divided by another function. Anytime this happens, you should try to use u substitution in order to integrate. Now, in order to use u substitution here, we got to set u equal to whichever function, if I were to take the derivative of it, would give me the other function. So you think you would be able to set u equal to cosine of x, and the derivative of that would give you negative sine of x. However, in this problem, this is in the denominator. So du would not account for this down here. So you can't do it that way. You have to set u equal to the denominator in this case. We're going to set u equal to sine of x plus 5. The reason is because if I take the derivative of this with respect to x, the derivative of u with respect to x is du dx. The derivative of sine of x with respect to x is going to be cosine of x. Derivative of 5 is going to be 0. Multiply both sides by dx, I get du is equal to cosine of x dx. So that takes care of this cosine of x in the numerator and this dx. Now what about this 4? Well, remember, this is just a constant being multiplied to our function. So technically, we could take that 4 and just move it out front of the integral sign. Then we can rewrite this integral in terms of u and du. We're going to substitute u in for sine of x plus 5. Du is going to go in for cosine of x dx. Now we have our integral that we can integrate in terms of u and du. How do we do that? Remember, the integral of 1 over u du in the theorem we talked about before is going to be the natural log of the absolute value of u plus c. Multiply that 4 on, and now all we have to do is take whatever we set u equal to, which in this case was sine of x plus 5, plug it back in for u, and we have our answer to this indefinite integral up here. Now let's talk about a special case. So we again want to find the indefinite integral. This time we have the indefinite integral of a rational function where the numerator and denominator are both functions. So normally in this case, what I would recommend is using u substitution to try to evaluate this indefinite integral. The only issue is, if I were to use u substitution, I would set u equal to whichever function, if I were to take the derivative of it, would give me the other function. So that would be this numerator up here. I would set u equal to x squared minus 4x minus 10. If I took the derivative of that, I would get 2x to the first first minus 4. Now, the only issue is down here, I have x plus 1, and it's 1 over x plus 1, right? Because it's in the denominator. So du would not account for this down here, meaning I can't use u substitution in order to integrate this. So what am I supposed to do when that occurs? Well, you need to simplify this rational function using division, and you can either use long division or synthetic division. Then you can integrate. So let me show you how this works. First, we're going to show you long division. Remember, long division is where you take your denominator, that's going to be your divisor, and you're going to divide it into your numerator, which is going to be your dividend. So it's going to look something like this. Now, the way long division works is I have a binomial here, which is going to go into a binomial right here. I need to figure out, what do I multiply this first term by in order to equal this first term? That's going to be x. So I'm going to put that right here because this binomial has to go into this binomial. Now, I'm going to distribute the x to the x over here and to the 1, and I put that product underneath these first two terms. Now I need to subtract, just like I do in normal division. What's x squared minus x squared? Those cancel out. That's what's supposed to happen. Negative 4x minus 1x is going to be negative 5x. We put that difference right here. Then we're going to bring down this negative 10 and repeat the process. What do I multiply this first term by in order to get it to be this first term? That would be negative 5. So I put negative 5 right here. I then distribute that negative 5 to the x and the 1 and put that product down here. I then subtract down, just like I did up here. What's negative 5x minus negative 5x? Those cancel out. That's why we did it. Then negative 10 minus negative 5 is going to be negative 5. This is going to be our remainder. Now, what do you do with a remainder? You tack it on the end and you put it over your divisor. So x squared minus 4x minus 10 divided by x plus 1 is going to be equal to x minus 5 minus 5 over x plus 1. You could also get the same result using synthetic division, which is my preferred method because there's fewer variables. So what you're going to do, your divisor here, x plus 1, is technically in the form x minus r. So your r in this case would be negative 1. That's what you're going to put in this little half box over here. And then next to it, you're going to put the coefficients of your dividend, 1, negative 4, and negative 10. Now what we do is we draw a little line underneath with this little bar right here to denote where our remainder is going to go. We drop down that first coefficient below the line, and we're going to multiply. Negative 1 times 1 gives you negative 1. We're going to put it under our next coefficient. Then we add down. Negative 4 plus negative 1 is going to give you negative 5. We then multiply. Negative 1 times negative 5. You get positive 5. Put it right here under your next coefficient. Add down, and you get negative 5 as your remainder. Well, the way synthetic division works is that we have down here the coefficients of our quotient. So we need to determine the variable and degree that goes next to each of these coefficients. So we're going to start with our leading coefficient, 1. The variable that goes next to that leading coefficient is going to be x. The question is, what power, what exponent are we going to put with that x? Well, you're going to start with 1 degree less than what your dividend was. So your degree in your dividend was 2. Therefore, you're going to start with x to the first. So it's going to be 1x to the first minus 5. And then your remainder is negative 5. So it's going to be minus 5 over your divisor, which is x plus 1. So either way, you end up getting this as your quotient. Now, why did we do this? Because this right here is much easier to integrate than this right here because we have a function with multiple terms. So we can just integrate each term separately. That's what we're going to do. Now let's prepare each of these for integration. This one's ready to go. This one, this constant, we can just move out front of our integral sign. This right here is a constant being multiplied to this function, so that can move out front of our integral sign. Now we're ready to go. The integral of x dx is going to be x squared over 2 plus c. The integral of dx is going to be x plus c. The integral of 1 over x plus 1 dx, remember we have x to the first in our denominator, we have 1 in our numerator. That means this is just going to be the natural log of the absolute value of our denominator, x plus 1 plus c. Now you can box this up as your answer, call it a day, or you could rewrite this with a 1/2 multiplied to our x squared to make it look a little nicer. Either way, this is the answer to our indefinite integral up here. Now example 3 says find the area of the region bounded by the graph of the given function, the x-axis, and the line x is equal to 3. So here's our given function, and this is what the graph looks like. Basically, all this is asking you to do is find the area under the curve from x is equal to 0 to x is equal to 3. In order to do that, we need to create a definite integral from x is equal to 0 to x is equal to 3 of this given function. Now all we have to do is integrate this, and that'll give us the exact area under the curve. So how do we integrate this? Well, we have a function being divided by another function, and anytime that occurs, you want to try to use u substitution in order to evaluate this integral. So we're going to set u equal to whichever function, if I were to take the derivative of it, would give me the other function. So I'm going to set u equal to x squared plus 1. The reason is because if I take the derivative of this with respect to x, derivative of u with respect to x is du dx. The derivative of x squared is going to be 2x to the first. Derivative of 1 is going to be 0. multiply both sides by dx, I get du is equal to 2x dx. And we look at the problem. There's an x and there's a dx, but there is no 2. So I need to divide that constant to the other side of this equation. And now I'm ready to rewrite this integral in terms of u and du. But before you start integrating, remember, you are using u substitution with a definite integral. Anytime that happens, you need to rewrite your limits of integration in terms of u. This is the biggest mistake made in this type of question. So let's rewrite our limits in terms of u. How do we do that? We start with our lower limit, x is equal to 0. We're going to take that and plug it in for x in whatever we set u equal to, which in this case was x squared plus 1. When we plug that in and simplify, we end up getting our new lower limit of integration is going to be 1. Do the same thing with our upper limit of integration, x is equal to 3. Plug that in for x in whatever we set u equal to, simplify, and we end up getting our new upper limit of integration is going to be 10. Now we can rewrite our integral in terms of u and du with our new limits of integration. So it's going to be the integral from 1 to 10 of, and I'm going to plug in u for x squared plus 1, and we're going to plug in 1/2 du for the x and the dx. Now all I have to do is prepare this for integration and then integrate. So I'm going to take this 1/2, move it out front of the integral sign. I then am going to evaluate this definite integral. Now, in order to evaluate a definite integral, we're going to use the fundamental theorem of calculus. In order to do that, the first step is to find the antiderivative of our given function here. So what's the antiderivative of 1 over u du? Well, we said it's going to be the natural log of the absolute value of u plus c. But because we're using the fundamental theorem of calculus, we don't need to include c because it technically cancels out during the fundamental theorem. So all that's left is to use the fundamental theorem of calculus in order to evaluate this. We're going to take our upper limit of integration, which is 10, plug it in for u, and subtract when we take our lower limit of integration, 1, and plug it in for u. We evaluate each of these, ln of 10, that's just ln of 10. ln of 1 we know is 0. We then simplify and we end up getting 1/2 of ln of 10 as our answer. Now you could leave your answer like this, or you could round it to the nearest thousandth because that's what it wants you to do on the calculator portion of the AP test. And that's going to be approximately 1.151. That is the exact area under the curve of this function on the interval from x is equal to 0 to x is equal to 3.
Queen ants have wings, and they lose them when they start a new nest. This is crazy. You try.
Okay, doing the same thing here. We want to find the area of the region bounded by our function, the x-axis, and the vertical lines x is equal to pi over 4 and x is equal to 3 pi over 4. So anytime you want to find the area between the function and the x-axis on a given interval, we need to create a definite integral. So the definite integral is going to have a lower limit of integration of x is equal to pi over 4 and an upper limit of integration of x is equal to 3 pi over 4. And it's going to be the integral of the function sine of x over 1 plus cosine of x. Now all we have to do to find this area is evaluate this definite integral. So how do we evaluate this type of function? Well, we have a rational function where we have a function in our numerator and denominator. Anytime that happens, you want to try to use u substitution in order to evaluate this. Now remember, you want to set u equal to whichever function, if you were to take the derivative of it, would give you the other function. So in this case, I'm going to set u equal to our denominator here, 1 plus cosine of x. The reason is because if I take the derivative of this with respect to x, I get the derivative of u with respect to x is going to be du dx. The derivative of 1 is going to be 0. The derivative of cosine of x is going to be negative sine of x. Multiply both sides by dx, I get du is equal to negative sine of x dx. We look up here, we have a sine of x and a dx, but it's not negative. So what we do is we take this constant, because it's technically negative 1 times sine of x dx, and divide that to the other side of this equation, and we get negative 1 du, or negative du, is equal to sine of x dx. Now we can substitute u and du in for all of the x's. Perfect. Remember though, you don't want to just go ahead and start integrating using the fundamental theorem of calculus. We use u substitution in a definite integral. Anytime that happens, you need to rewrite your limits of integration. So I'm going to take my lower limit of integration, which is going to be pi over 4, and I'm going to plug it in for x in whatever I set u equal to. When I do that and simplify, I end up getting my new lower limit of integration is going to be 1 plus rad 2 over 2. I then do the same thing for my upper limit of integration, 3 pi over 4. Plug that in for x in whatever I set u equal to, simplify, and I get my new upper limit of integration is going to be 1 minus rad 2 over 2. Now that I've rewritten my limits of integration, I can rewrite this definite integral up here with my new limits of integration in terms of u and du. I'm going to take u and plug it in for 1 plus cosine of x. I'm going to take negative 1 du and plug it in for sine x dx. I'm going to take 1 plus rad 2 over 2, make that my new lower limit of integration. I'm going to take 1 minus rad 2 over 2, make that my new upper limit of integration. Now I have totally rewritten this integral up here in terms of u and du. So all I have to do is evaluate this using the fundamental theorem of calculus. How do we do that? Well, let's first prepare this for integration. I'm going to take this negative 1, move it out front of the integral sign. Now I'm ready to evaluate this using the fundamental theorem of calculus. My first step in using the fundamental fundamental theorem calculus is to find the antiderivative of my given function. So what's the antiderivative of 1 over u du? Well, that's going to be the natural log of the absolute value of u plus c. We then tack on that negative out front, and now we can evaluate this using the fundamental theorem of calculus. Remember, we don't have to include the plus c because it cancels out during the fundamental theorem of calculus. So how do we do this? Well, I'm going to take my upper limit of integration, plug it in for u, and subtract when I take my lower limit of integration, plug it in for u. I then plug all of this into my calculator, and I get that the area under the curve of this function on this given interval is approximately equal to 1.763. Remember, rounding to the nearest thousandth because that's what it wants you to do on the calculator portion of the AP test. Now, one final note. If you noticed, our lower limit of integration is actually greater than our upper limit of integration. And normally when that happens, you have to switch these and put a negative sign out front. But this is the one scenario where you're allowed to leave it like this when you're using u substitution and rewrite your limits of integration. When that happens and your lower limit of integration is greater than your upper limit of integration, you can actually just leave it like that and evaluate it like normal. This is the only time you're allowed to do that.